Hi class, we are on section 8.5 now. This is polar equations and graphs. So we are going to focus on equations in polar form. So we'll have lots of r's and thetas and sines and cosines. We'll focus on taking a graph, or I'm sorry, an equation in rectangular coordinates. Y equals 3x plus 2, for instance, right? The equation of a line. And looking at that in polar form. What would that look like as a polar equation, right? So again, we're just going to revisit the polar coordinate system with graphs of polar equations and converting from polar to rectangular equations and vice versa, and classifying certain common equations that show up in our polar forms. Okay, so the polar coordinate system is based on a point, just like the rectangular coordinate system, right? So for the rectangular coordinate system, you have an x-axis and a y-axis, and any point in that space you find by going over a distance of x and up or down or what have you, a distance of y, and that's how you get to your point. In the polar coordinate system is very similar. What we do is we talk about everything in terms of r and theta, right? How far of a radius do I have to go out? And then at what angle do I need to sweep to get to that same point that I would find as an x and y coordinate in the rectangular system? So the x-y coordinate, the rectangular coordinate system and the polar system, they're the same. Sometimes the rectangular system is better to use than the polar. Sometimes the polar is better to use than the rectangular system. That's why we have two different coordinate systems. We actually have quite a few different coordinate systems, and a single point can be referenced in any of those coordinate systems, right? So that's really what we're focusing on today. We're just starting with a point and talking about it in terms of, instead of x and y, talking about in terms of r and theta, right? So that point in the polar coordinate system we call a pole, right? Then there is a ray that is going to come from that pole, which is our polar axis, right? And a point P, which is given by xy. Instead of talking about going over x and up y, we can talk about swinging out our polar axis some distance of r and then sweeping it up in an angle and creating an angle of theta. Okay, right? So again, we go over, normally we would go over x and up y in the rectangular coordinate system to get to this point. However, in terms of r and theta, as I said before, we are going out a distance of r and then sweeping up a radius, an angle of theta. So instead of calling it x and y, right, I'm calling it r theta, right? So r obviously has to be positive, it's greater than 0, and then we just talk about its angle in whichever direction I have to go, right? So this is the polar coordinates, r theta, and this is the exact same point in rectangular coordinates as x, y, right? Generally, when we do polar coordinates, instead of having a bunch of square grids like the rectangular coordinate system, we usually have lines for, to trace our radii, but then we have our circles since we're going out a distance and then we're tracing an angle. So we have the circles to help us trace out the angles that the radius to our given point has to go, right? Angle that gets swept. So if r is positive, then the point P lies on the terminal side of theta. If r is negative, right, less than 0, then P lies on the ray pointing in the opposite direction. So instead of going positive direction of r and sweeping in an angle, we can go positive direction of r, sweep our angle, and then call r the negative direction, and then we can end up over here instead of being in the positive. So we still sweep that direction, but we just take r to be in the opposite direction, the same length. Okay, so it's always the same distance of r, it just happens to be in the opposite direction, right? So rectangular polar coordinates. So if a point has rectangular coordinates of x, y, and polar coordinates r theta, these things are related to each other, right? And they are related by x equaling r cosine theta, y being r sine theta, and r squared being x squared plus y squared, or another way of thinking of that is that r equals the square root of x squared plus y squared, or very similar to how we would generally find the modulus or the length of a side, the Pythagorean theorem basically, right? And again, theta is tan inverse of y over x, right? So again, all of these things are something familiar to us. We've seen these relations at the beginning of this chapter. So we're using those same relationships in order to be able to convert from rectangular to polar coordinates, and also from polar coordinates to rectangular coordinates, okay? So let's do an example. So let's plot each by hand, right? So if I ask you this on an exam or a quiz, I would like to see this worked out, all of your work shown, obviously, right? So we want to plot each point by hand in the polar coordinate system. Then we want to determine the rectangular coordinates of each point, okay? So here I have a radius of length 2, and I'm sweeping an angle of 30 degrees, and then once I plot this, I want to find what its equivalent point would be in terms of x, y, right? The rectangular coordinate system, okay? So here r is 2, theta is 30 degrees, so p is 2 units from the origin in the positive direction, and then we sweep an angle of 30 degrees. So we want to use the relationships that we have that between r and theta, and use that, right? I know r and theta, so I can find x by using this relationship. I know r and theta, so I can find y using this relationship as well, right? Okay, so again, I want to go over a distance of 2 and sweep up an angle of 30 degrees, okay? So using my conversions, x is r cosine, r is 2, theta is 30, so I just find the value, the exact value of cosine 30 degrees, and I plug that in. The 2's cancel, so I get x is square root of 3. Same thing for y. If this is root 3 over 2, then this is going to be 1/2, right? So that will give me a y value of 1. Okay, so then the coordinate in the rectangular system is root 3 comma 1 is equivalent to 2 comma 30 degrees, or 2 comma pi over 6 if we're using radians, in the polar coordinate system. Okay, so these are the rectangular coordinates for that point in polar coordinates. Okay, b is the same thing. Here, instead of degrees, is giving us the radian measure, and it's saying I'm in -4, right? So I would still go this, I'll go over 4, I would still sweep 2 pi over 3 as an angle, and then I would move 4 in the opposite direction. Okay, so r is negative, so it's going to say the same thing. We do what we normally do, and then we sweep in the opposite direction. Okay, so I would go out a distance of 4, right? So you got 1, 2, 3, 4. You sweep it 2 pi over 3, and then we go in the opposite direction. Okay, so here to plug into my formula for my conversion, right? I plug these in, I get -4 times -1/2, so I get 2. For y, it'll be the same thing, -4 times negative root 3 over 2, right? Or positive root 3 over 2, I'm sorry. Because even though I'm over here, the angle that I'm using is still in this quadrant, right? And so when I simplify this, it's -2 root 3. So my coordinate is 2 comma -2 root 3, and again we can just make sure we're in the right quadrant, right? So this is positive x direction, negative y direction, that coincides with the correct quadrant that my point lies in. So that's just a quick check to make sure I'm at least in the correct ballpark of what it is I'm trying to do, right? So put those two together, and that is my correct point. Okay, same thing here. So we have a radius of 5 and an angle of -pi/4. So we would go down 45 degrees. Okay, all right, and a distance of 5. right? So we want to find out what this point is, so we do the same thing we did before. X is r cosine theta, y is r sine theta. Okay, so we get 5 root 2 over 2. Okay, and for sine, we basically get the same thing, but negative, because this point is at pi over 4, right? But negative, so it's point without the extension of 5 is root 2 over 2, negative root 2 over 2. Then we multiply by 5 because we are extending out the radius, right, from the unit circle. So those are our rectangular coordinates. Okay. So quick note: while a given point in the plane can have only one pair of rectangular coordinates, it can have an infinite number of polar coordinates, because you can always go around the circle 1, 2, 3, 20 times in order to end up at the same point, right? We're going in a circle, so it doesn't really matter how many times you go in a circle as long as you end up in the same spot. Okay, so there's equivalent points for polar coordinates, but there's only one single point in rectangular coordinates. Okay, so we generally obviously write the lowest value angle, the coterminal value that we need for our polar coordinates. Okay, so they want us to give 3 other pairs of polar coordinates for the point 3, 140 degrees. So really the easiest way to do this is you take 140 and then you add 360 to it, add another 360 to it. You can even go 140 minus 360 if you want to throw a negative angle in there, if you so choose, right? Negative 220 degrees. Okay, so and then also you can also use a negative radius, which I didn't even think about until we just showed this, right? So I can go, hey, let's go negative 40 and 3, and then just go in the opposite direction 3, and we'll still end up at that point, right? So you can kind of either just add a bunch of 360s to it, or you can start to use the negative radius value as well. Okay. So B, determine 2 pairs of polar coordinates for the point with the rectangular coordinates of negative 1, 1. Okay, so the easiest thing to do is find the first polar coordinate that we've been doing before, and then the second would be to do the same thing, but either adding 360 to the angle or finding an equivalent angle and then going in the opposite radius direction, right? Both of those are semi-easy. So we have negative 1, 1. Obviously this lies on a 45 degree, so just by looking at this you can tell that this should be a reference angle of 45 in the quadrant 2, right? Okay, so that's the 135 degree with the reference angle of 45. So the radius here, we can use our formula for r, right? Square root of x squared plus y squared, so that's going to be root 2. And so 2 pairs of polar coordinates is going to be root 2, 135, and the other one would be negative 45 and negative root 2, right? That'll bring me down here, and then I can just go in the opposite direction. Or I can say, and this is just me trying to use a negative root 2, is I can say I want to go 315 degrees and then negative root 2. That's another way of doing it. Or I can say root 2 and 135 plus the 360, right? There's several ways in order to do this, right? So again, I can say 315 and then go negative 2. Okay, so I gave you 4, and they're all fairly straightforward, right? Okay, so graphs of polar equations. So an equation in which r and theta are the variables is a polar equation. So in the rectangular coordinate system, x and y, which is how we define points, those are our 2 variables, right? So in polar equations, r and theta are our 2 variables, right? One is the dependent and one is the independent, just like x and y. X is independent and y is dependent. For polar equations, it's actually reversed. So in the rectangular system, it goes x first, then y. In the polar equations, it's r and then theta. However, in the rectangular, the first one is the independent variable, the one that changes, and y is the dependent variable, the one that depends on the one that changes. In polar equations, it's opposite. The first one is actually the dependent variable, and theta is the one that changes. So the second variable is the one that changes, and my radius is going to change depending on the angle that I'm given. Okay, so define the polar equation of the line ax plus by equals c, or y equals mx plus b. Switch, if we move this around, as follows. So remember, x is r cosine theta, y is r sine theta. So we have to put in that substitution, and then we basically solve for r. R is what we want on one side, everything else on the other. Just like here, I generally would solve for y, put everything else on the other side of the equation. So what we're going to do is we're going to make these substitutions and then solve for r, right? So we're going to factor out this r because it's a common term here. So I'll have r times a cosine theta plus b sine theta. Okay, and then I can divide this on both sides. Okay, so my radius is, for a line in fact, is c divided by this value, a cosine theta plus b sine theta. So we're going to define the polar equation of the circle as x squared plus y squared equals a squared, where a is the radius of the circle, right? So again, we just make that substitution. Okay, we know r squared is x squared plus y squared, so instead of going r cosine theta squared, r sine theta squared, we can make this substitution as r squared equals a squared, which is exactly what it just said, right? It's r squared. A is the radius, so if this is the radius of the circle, there you go, right? So r equals plus or minus a when we square root both sides. Okay, and that's why it's polar equations, because everything we're doing is in terms of a radius and a circle, right? For each so let's go back there. Okay, so if the radius is a constant, right? If I say r equals 5, well, it makes sense that it's a circle of radius 5, right? If you think about it that way. Okay. So example 3: for each rectangular equation, give the equivalent polar equation and sketch its graph. Okay, so again, instead of taking the rectangular form, x's and y's, and graphing that, we're going to turn it into polar, and we're going to graph the polar equation. Okay, so sometimes this translates very well from a rectangular equation to a polar equation. Most of the time, though, it does not, right? Circles and ellipses, those are great in polar coordinates because it has to do with the radius and an angle. The equation of a line, as we saw, is terrible, right? That's a terrible function to have to try to graph. Okay, r equals some constant divided by a constant times cosine plus a constant times sine. That doesn't look very fun to try to graph, right? A circle, however, super easy, right? It's just r equals some constant term. So circles and ellipses are nice. Equations of lines, curves, parabolas, those are terrible. Okay, so the easiest things to graph in polar coordinates are any things that have a lot of curvature to them, right? Again, circles, ellipses, and other things as will come across in this video that you probably have never heard of, right? There's other coordinate systems that are similar to polar coordinates. One is called cylindrical coordinates, and that's very good for drawing circles as well, and spheres and things like that. We won't talk about that until Calculus 3, however, but there are other coordinate systems out there that are used for certain things, right? Anything that, again, that has a circle to it is easy to draw in polar coordinates. So that's when we would transfer over to polar coordinates, okay? So let's say I want to graph the line y equals x minus 3. I need to make my substitutions for y and for x, right? R sine theta, r cosine theta, okay? And once I've done that, I basically do the same thing and pull out my factor of r, isolate r, and get r is 3 divided by cosine theta minus sine theta. Okay, so if you didn't notice, what I did here is you could have just plugged it in position where it was, right? R sine theta, r cosine theta minus 3, that's fine, but they chose to rewrite it a little bit, basically getting all your variables on one side. That just made it easy for us to factor out the r later, because even if I wrote it on both sides of the equal sign, I would still have to move them over so I could factor out the r, right? So they just did it beforehand before it got kind of weird, okay? So this is the equation of a line, y equals x minus 3, okay? So this equation is equivalent to this equation where theta is my independent variable, the one that changes on its own, right? And r, my radius, depends on whatever value I have plugged in for theta at that time, okay? So again, this is how I graph the line in my regular rectangular coordinate system, and then if you overlay the polar coordinate system behind it, you will see that as well, okay? So I'm gonna switch gears real quick. Abracadabra, we're in a new coordinate system. I just wanted to show to you guys in Desmos that you can change your graph settings into polar coordinate system, okay? You can keep it in radians or degrees, but now it makes it easy for us to graph things, right? So if I wanted to do a circle, so let's go ahead and extend this out a little bit. I don't know what this will look like to you guys. Okay, but if I play around with this a little bit, like r equals 2, I'm going to get a circle of radius 2 because the radius is unchanging. Okay, now if I were to say theta, so as my theta changes, right, as theta is an angle of 0, my radius is 0. When theta is an angle of, I don't know, pi over 53, my radius is whatever the value of pi over 53 is, right? So as my angle gets bigger, my radius gets bigger, right? Smaller and smaller and larger radius, I'm sorry. So as the angle gets larger, so for instance, for this ray right here, okay, I have quite a large angle, and my radius is the same as my angle size, right? So as my radius is growing, I'm also moving in an angle that is getting bigger and bigger. So it starts to swirl around and grow. I can even make it a little bit tighter by saying that my radius is twice the length of my angle, right? So then it doesn't swirl as much. All right, if I go 1/2, it swirls twice as fast. Okay, and come over here and say r equals 2 theta, right? And then a base of r equals theta, right? So the green is a basic swirl. If I want to swirl in half the amount of time, then I do my shift, which means go half as slow, right? So the swirl is half as much, okay? If I want to swirl twice as fast, then I say every time I have a theta, my radius is basically going to be double whatever the theta is, right? If I were to solve for theta, that's what this would look like. So now the spiral is twice as fast, okay? So again, things in the polar system are pretty cool when you start to learn how to manipulate them, right? So I can start to do some crazier things here. So again, you know, I'm just showing you some things that you could do to play with, right? So I'll come back to this. We'll do another quick exploration here once we get a little bit better. But let's go ahead and look at even one of the ones that we just looked at, right? Which was r equals 3 divided by, and we had cosine theta plus sine theta. And we had a line, right? So you can double check and play around on Desmos if you want to see and make sure you have the same kind of graphs, okay? Okay, and so if you notice that my graph was a little bit different from this because I just went off my memory and I put 3 cosine theta plus sine theta, so that's why we had a slightly different slope than what we had here. But this general form that we got to see here, things that look like this are equations of lines, right? Things that look like this, r equals some constant, that will give you a circle. Okay. Alright, so y equals x minus 3 in rectangular coordinates, or r equals 3 over cosine theta minus sine theta in polar coordinates is equivalent. Okay. Here we should know right away that this is the equation of a circle with the radius of 2, x squared plus y squared equals r squared, right? 4 is 2 squared. So again, making that substitution that r squared equals x squared plus y squared, it's very, very easy to know what this substitution is, right? It's basically r is either plus 2 or r equals negative 2. It doesn't matter. It'll be the same thing. It's just, do you want to start off with going out this way 2 and then going in a circle forever, or do you want to start off and going this way 2 and going in a circle forever? It doesn't really matter. You're still going to get a circle of radius 2, right? Okay, so again, notice that r can be negative, and that's fine, right? Either way, you will get this image, which is actually what we graphed when I did it. Okay, so this is the equation in rectangular coordinates, and that's the equation in polar. So now we can do what's called a cardioid. Okay, I never can say a lot of these right. A cardioid, right? So cardioid is r equals 1 plus cosine theta. Okay, so again, there's always going to be cosines and sines, possibly tangents, a lot of trig functions in these polar equations, I'm sorry, right? So here again, my radius changes as the angle changes, okay? So I want to find some ordered pairs to determine the pattern of values of r. So again, you're not always going to have Desmos with you. Possibly, maybe you forget your calculator at home. Whenever we get back to regular life, by the way, this is all filmed during COVID, for future generations that watch my video for some other class, right? So we weren't in the classroom at the time. So, you know, whenever we do return to normal, possibly you forget your calculator and you have to do this by hand, right? So it's nice to know how to do things because stuff like that does happen. Your calculator dies, the batteries die. I have definitely been on very large exams where I have no calculator and now I have to remember how to do everything off the top of my head. You know, it happens. So you don't want to get reliant on your calculator, but you want to know how to use it, right? So if you don't have your calculator, for instance, what you would do is you just choose random values of theta. And when I say random, I don't really mean random. I mean use the standard values that we have, right? Pi over 6, pi over 3, pi over 4, pi over 2, 2 pi over 3, right? Just go through your unit circle. You don't have to do all of them, but you want to get a good idea, okay? Now, even though it may be patternistic, it's not like the equation of a line where it's very patternistic, right? These things are curves. They tend to curves as you go through the circle. The values will change, right? So it may be possible, and we'll see this, that through 0 through 2 pi, I get one set of values, and then they do not repeat again from 2 pi to 4 pi, the next set of the next circle, right? From 0 to 360, it's one set of values. From 360 to 720, or 740, it's a completely different set of values, right? So when we do these, we want to make sure that generally we go through enough values to get a good idea of what's going to happen, right? So here, let's start with a table. I plug in pi is a theta, okay? And then once I have that, I'll find the value for cosine of theta, and then I'll just add 1 to those, so then I can have my inputs and my outputs, right? So I'm just slowly building this function, right? So 0 degrees gives me a cosine of 1. Add 1 to that, I get 2, right? For 30 degrees, I'm going to get 0.9, right? Or root 3 over 2. I'm going to add 1 to that, okay? 45 is going to be root 2 over 2. I'll find the decimal approximation. I'll add 1 to that, right? And so forth through everything, okay? Through a few values. So as you notice, I'm kind of going through almost to 180. I mean, you know, you'll get tired of this, so I'm finding some values, okay? So you notice there's not really a pattern here for the output values, okay? So continue to go through and get some values, right? Let's go a little faster. So I basically went through 360 almost, okay? And there's a little bit of repetition here, a little bit of symmetry, okay? But not, I mean, there's still values that I would never be able to guess, okay? So now that I have a few of these, I would connect these in a line, and then now this is the curve that I have, okay? Abracadabra, okay? So right now, we are looking at what happens when we have r basically equals 2 right now, right? So when I had something that looked like this, I had my cardioid, okay? So what I'm doing right now is I have the equation that we wanted, okay? I put cosine A times my theta value, okay? So when I had 0, okay, a little bit more, I got 1 plus cosine of basically 0, which is 1. So 1 plus 1 is 2. That's a radius of 2. Okay. When I plugged in a value of 1, I got the cardioid that we just graphed. Okay. So what I'm going to do is I'm going to allow this to play, and we can look at some of the different shapes that get taken on when I have different values being multiplied times my alpha. Right. So it kind of looks like we form a daisy with increasing number of petals as my A value gets large, absolute value wise. And if you notice, we also start to get sort of a curl that we had before, okay? So when we are about here, right, we have somewhat of a curl. So remember when I did radius times my angle? That's because now I have 1/2 of theta, right? So it looks very much like a snail's shell, actually, if you think about that, okay? And we can change ourselves back to the grid values, and we still have the same shape because of the function that we're using. We're not using x's and y's, we're using r's and thetas, but now the backlay is now the rectangular coordinate system, which doesn't really match with what we're doing, but it doesn't change the shape of my function, okay? So just some things to play around with. And then remember what I said about going from 0 to 2 pi. If we increase this to, let's say, 4 pi, we'll get completely different shapes for the same function that I had before, right? So if I look at different values, different domains, instead of stopping at once around the unit circle, I will get different images, right? Now, let's say I go to pi, for instance. I'm only going to the first upper half. I will get different values as well, right? So my domain, the restriction on my domain, actually changes what it is that my graphs are going to look like, right? Right. So if I change this, is even different than before. So there's numerous things in the polar equation world which will change my graphs, right? So I can get very nice, cool looking graphs. Okay. If you're a kid and you ever did a spiral graph, you know, you get a lot of these same sort of shapes that pop up. Okay. But there's very cool sort of pictures that get to come out of these types of graphs. They're very beautiful. So from what we had over here, right, trying to graph by hand, this is ideally the image that we can come up with, right? It's called a cardioid. And the curve has been graphed on a polar grid, right, which is what we were using. And we can change what our windows look like, how far out, right? Do we want to go all the way to 10 and -10 like I did before? Or do we want to change the window to fit a little bit better? You can always use your window button to change your step size, right? Which you saw me doing with Desmos. Things of that nature, right? So here's another one. We're going to graph r equals 3 cosine 2 theta. So again, very similar to what I did in the previous exploration. If I had done sine instead of cosine, I would have got something different, right? So at the end of this video, I'll play around a little bit. I suggest you do the same. There's some really cool things you can get out of these graphs, right? So here we're going to graph 3 equals cosine 2 theta. Again, we're going to find some points. I'm just going to go quickly through these because I'm sure you don't want me to talk about every single one of these squares, right? So here will be our angle measures, okay? Here will be cosine 2 theta, 3 times cosine 2 theta, right? So we'll kind of just find these things one at a time, right? So find my angles, double those angles, plug these angles into cosine, and then take the values I get out and multiply them by 3. Okay, so if we graph this, it'll be similar to something that we saw already. So you get this 4-leafed rows. Okay, You can graph that on your calculator as well. And then again, notice it's a continuous curve, right? So they have your starting point, right? So you start here and they're telling you this is the first one, right? Then this is the second one, and the third, and the fourth, and the fifth, the sixth, and the seventh, and then the eighth to finish, right? So they're telling you the order in which this thing goes. Even though you're going clockwise, these are the values that you will be getting out, okay? All right, so graph. Here we want to graph r squared equals cosine 2 theta. So we saw cosine 2 theta already in the Desmos. We will now be doing the square root of that, right? So again, same thing, start with our thetas, double those values, okay? Take the cosine of those double values and then square root them, okay? And we'll calculate the positive and the negative values for those, right? So values for 45 through 135 are not included in the table because the corresponding values of 2 theta are negative, right? So values for theta larger than 180 are given, and they give 2 theta larger than 360, and they would repeat themselves. So basically what they're saying here is that they are not including the values that basically just repeat themselves. So they're giving you values that give you unique values, right? So they're not going over 180 because for 2 theta you're just gonna double those values, right? And so in between this portion of it, you're basically on the positive and the negative side of being square. So when you square it, it comes out positive anyway, so it doesn't matter, okay? So this is going to give you the infinity symbol, right? If we're squaring the output that we get, okay? So if we want to graph this, it's called the lemniscate, okay? We got to graph both halves, the positive portion and the negative portion, because r squared is now saying you're going to take the outputs and square them, so even the negatives get turned positive, which is again why they said that they weren't putting in the values in between 45 and 135 degrees, okay? Because for those cosine values, you're just doubling yourself, right? So you plug in both the positive and the negative square roots, okay? And it'll look like this when you say y equals on your calculators, and it'll give you the infinity symbol, okay? Here, if I want to graph r equals 2 theta, we actually did this as well. We're going to get that loose spiral, right? We get the loose spiral, okay? So we can go to these values. If we did it by hand, we go through several values, okay, all the way to 2 pi. And these, again, are pretty much the standard values that we use, right? And we will get something that looks like this, right? Call this the spiral of Archimedes. Okay, and so for there we go. Okay, and if I want to convert the equation r equals 4 over 1 plus sine theta to rectangular coordinates and graph, so remember what these are, right? So we went over some polar hyperbolas, some quadratics, some things like this, right? Polar forms of those. And that's basically what this is, right? If you remember, this is a polar form. So we can put this into rectangular coordinates by going back, right? I know that if I multiply this times this, I'll get r plus r sine theta if I clear this denominator, okay? So I can start to make some substitutions, okay? I know r sine theta is y. Okay. I know r is the square root of x squared plus y squared. Okay. Start to try to solve for y, because this is very confusing. This doesn't really give me too much information. So really what I would do here is I would square both sides. So x squared plus y squared is 4 minus y squared, and expand this. Okay. And then I got a y squared and a y squared, so that can cancel. And I basically get solving for y. In this case, really we would want to solve for x squared. I get x squared is 16 minus 8 y. Okay. And now I'm in a rectangular equation. If I want, I can solve for y, right? And say y is x squared minus 16, that whole thing divided by 8, which is a quadratic, right? So this is a parabola. Okay. All right, so here they solve for x squared, but if you solve for y, it's very clear that you have an equation that is a parabola. Okay. All right, so some classifications. So circles and lemniscates. Lemniscates are circles, but then they may have some curves in the middle of them, right? Okay, so here's just some common ones. So r equals a cosine will be a circle or an ellipse on quadrants 1 and 4. If you're using sines, you're going to have the positive value of sine here. You have the positive values of cosine covered, right? Positive values of sine, so it's in quadrants 1 and 2. Here will be a mixture, okay? Cosines will be an infinity symbol like this, all right? Limicons, have these sort of equations, a plus or minus b sine or a plus or minus b cosine, okay? And so these will have the little loops in the middle, okay? They look like cardioids and things like that, okay? Rose curves, right? So we looked at quite a few curves that were rows. So sine n theta, right? Cosine n thetas, right? So we look at these kinds of things. So for sines, they're a little bit different. And of course, n being even gives you different types of roses, right? And if you have odds, you have different types of roses as well, right?